It does look like we're good to go. So, thank you, YouTube. We are good to go. Hopefully this time around we won't have the major issues with the microphone, and I'm hoping that it is on and working. There's a green light and the mic levels look good. Okay, so this extra session is just to try and get through the same amount as if we were doing it weekly, because I'll be going on holiday. So that's going to be fun. And obviously this is the time, the last 2 weeks, where you're probably going to be revising and it's feeling like there's a lot of pressure right now. So best of luck to everyone, and hang in there. That steady bit of work is going to pay off. So this session is session 11. I had to call it something, and I just thought I'd go with quadratic sequences and algebraic fractions. But as you can see, there's a lot more. We have quadratic sequences, simultaneous equations, which is the quadratic kind, rearranging equations, and algebraic fractions. So 32 days to go, by my reckoning. At least I put in Google and asked it how long there was until the first date of the exam, and I'm hoping it's correct. But does it matter? We're just trying our best every single day, right? And if you want to get these questions ahead of time, please go to Patreon. They will be there. What I'm thinking over these next 2 weeks is it's a good chance to do semi-exam question, like a set of questions, just to make sure that we're on track. I think the questions we're doing in these live sessions are really useful, quite challenging sometimes, and definitely unique because I've made them all. There's also a document that I've made that goes over all the basic, and two quite complex, but I would say the most important topics, and that's what's going to be on Patreon this week, ready for the session when I get back, which will be when would that be? That's how we look there. Yeah, so maybe the 28th. I think that'll be another Sunday. But just to look out, not many people come to the live. Most people are watching this not live, if that makes sense. And so, just check in after Sunday. Anyway, welcome, and let's get started. I want to set this up like this. And this is me just arranging my other screens because there are 3 to do this. I need to monitor a few different programs to help us go live. Okay, question number 1. Now I'm trying this whole thing about drawing the questions bigger. I think it prints out better. I make all of these in S-Note, and the computer version of S-Note, at least as far as I'm aware, is not being supported anymore. So I'm using this workaround, I should call it, and when it turns it to a PDF, it's not as crisp as the ones on the tablet, so I figured I just need to make it bigger. And then, so we're not going to be writing that big, perhaps. Here's our first anomaly. Is that a record? We haven't even written a number yet. Let's just get started. So what is this doing here? Well, it's algebraic fractions. It's also a bit of quadratics. Like you'll notice, now that we've got the basics out of the way, whenever algebra comes up, it's a lot to do with quadratics. So we need to get good at quadratics. And this is no exception. Now, how could I tell this is going that way? Well, we have to solve this. And I can see a couple of x's in a couple of locations. It's just likely that I know if I'm going to add these two together, I'm going to be expanding a double bracket that will give me a quadratic. Let's see if I'm wrong. And happy to be. So where should we start? We'll start on the right hand side. So this is an algebraic fraction. It has a denominator. Usually if we are adding fractions like this, we would have to have a common denominator. Now it's all very well if there's 3 and a 4, because we know that what 3 and 4 go into. We know the times tables. We don't have any clue about the size of these because they're an unknown. So in this case, we're going to have to do a method which is surely going to get us there. For example, if we had denominators of 8 and 5, is this a good example? No, let's do 10 and 5. Now these two, clearly the common denominator is 10, so we just multiply this by 2. But if we had a method that would definitely guarantee that they were a common denominator despite it being the quickest, then we could multiply them together and say 10 times 5 is 50. And this is surely going to give us a common denominator if we do these to both sides. But it's not going to be the best common denominator. As we know, 10 is a smaller number, and therefore 50 is going to be harder to work with. So in this case, we have no choice. When it's algebra, we have to multiply them together. So let's just make a note that in algebra, the common denominator is where we multiply these two together like this. And that's as good as we can manage. We just have to deal with the fallout there. Okay, so if this is a common denominator, how do we get it on the left-hand side? Because clearly this left-hand side is not quite where we want it to be. Let's just draw it. And we think what we want is an x minus 1 there. In essence, we're multiplying by x minus 1 on the bottom to get what we want. But whatever we do to the bottom, we have to do to the top. So this becomes x minus 1, like that. And I've done a pretty good video on this already, where we're adding fractions, algebraic fractions. It gets a bit harder than this, but it's the same principle. It shouldn't be too difficult if we're just thinking about what we haven't got and then adding it on the top and the bottom. And the same for the right hand side. Well, we've got an x minus 1, and when I say got, I mean we've got it as a factor. And what we're missing is the 3x minus 2. Well, we're going to need that on the top as well. So that's 1 times 3x minus 2. And it is just the same as with numbers, where you times the top and the bottom by the same thing. This time it's algebra. So slightly different, but not altogether different. And now we have a license to add these together. And not wanting to skip any step, I'm just going to do one thing and see where we are. There's our common denominator, and we're going to be adding 8x minus 1 and one lot of 3x minus 2, so we'll just leave it like that. I'm keeping my structure. My next stage is to expand the brackets like this. Now technically these two brackets here don't need to exist because it's all add and subtract. Or should I say add or subtract? But we'll leave it there. 8x subtract 8 plus 3x subtract 2. Now we've got a bit of time and headspace to check if anyone's online. I remember a couple of people came a few weeks back and I didn't look, so I'm just going to keep my eye out this time just in case. I could be my own fan and put some hearts in the chat. How do we do this? Get rid of the... Yeah, never mind. We'll carry on. At this point we're going to be adding like terms. So we've got the 8x and the 3x. It's 11x. And then minus 10. We will just leave it at that for now. We can take as long as we want here to get to it. The most important thing is not to make a mistake. That could cost us a lot of time. Now, at this stage, we're trying to solve it and we want to get x on its own. So let's not forget what we're doing here. Alternatively, you could say, I'm just doing whatever it is I'm capable of doing. I mean, I don't know if this is going to lead to the final result that I want. I'm just kind of going to trust it and keep going. There really is only one thing I could do here. Well, there's two. I could expand these brackets at the bottom, or I could get rid of the fraction, which is always important when trying to rearrange this to get x on its own. So I'm going to get rid of that fraction by multiplying by both of those fractions at the same time. And you're going to imagine that it's just one thing that I'm multiplying by on both sides. So rather than actually one copy would be better. So I'm going to multiply both sides. And what we end up with is the left-hand side denominator just cancels, just disappears. And on the right-hand side, we have -1 lots of 3x minus 2. So it's much quicker to write on paper. Get less of the delay, which is causing the issue here. Well, now we're looking to get x on its own still. We're looking a bit better here because we have one line, no fractions. And unfortunately, the inevitable must occur. We must expand these brackets here. But I've got to move this over first. How do I move that over? I could divide or multiply both sides by -1. What's going to happen on the left-hand side? Well, this -10 is going to become +10. This +11x is going to become -11x. If we divide by 1, you see it changes nothing about the size, but this sign is going to change the other signs. And on the right, we could expand these brackets at the same time. So the 3x times the x, like so. I mean, it depends how you do it. I tend to generally do it with the box method in the exam to be sure, but you know how confident you are. So 3x squared, -2x, and -3x. So -5x and then +2. Because double negative there. And we can hopefully start to see that this is turning into a quadratic. A quadratic equation is one where we have an equal sign sometimes, but I suppose that's what makes it an equation. But the quadratic part is that the highest order of the variable is 2. Quadratic is a second order equation. So whenever you see x squared, it's go time. Now, there are a number of ways of dealing with a quadratic. The best is where it's just 3x squared plus 5x equals 0. That's really good. The harder one is where we have a number involved. So these three are not so straightforward. We have to use something called quadratic methods. So let's have a look. We're going to move all of this stuff around so it's all on the same side. I want to keep my leading term, the 3x squared, positive. So this side is going to stay. That means this is going to move over to this side. The way we do that is we're going to add 11x to both sides. So then we'll end up with 10 equals 3x squared. Oh, yeah, I just forgot I'm going to be adding 6x. And then I'm going to take away 10 from both sides. And it gives us, I'm going to switch this around. We're used to seeing like from left to right. So this, I'm just going to write it on the left-hand side. If I took away 10, I would end up with -8 and then nothing. Because if I took away 10 from here, it becomes 0. But I want to write the left-hand side on the right-hand side. It's fine as long as this equals this, then it doesn't matter which way around we do it. This is a quadratic. We could spend a while figuring out if we can factorize this straight away using our mind power. And you probably would start with something like this and quickly realize that our factors of 1, 8, 2, and 4 can't really get us to 6. We could do 2 times 3, which is 6. No good. 3 plus 8. They're not really doing it if you go through your combinations in your head. If you really are not wanting to waste time, we could do discriminant analysis, where we take the b squared minus 4ac part of the quadratic formula and we see what's going on. So that'd be 36. Take away 4 times 3 times -8. Well, this is going to be 12 times a negative, so 96, -96. So it'll actually be plus 96, like so. And those two together, 132, meaning we're going to have the square root of 132. It's actually not a very nice number, but it does exist because this is more than 0. Therefore, there are roots here and it's solvable, but it's just not very nice numbers. So if you want to know what this test is, it's called the discriminant. And we're about to use this potentially, well, at least part of it, in the quadratic formula to solve this wee thing here. Because the factorizing, it failed us. This one is a test to see if it's even possible without going and spending ages on a method and then realizing it's wrong. And we can actually solve this completing the square, but it'd be awful. You see all these little things here are quadratic methods, right? Completing the square. But the one that we're going to use today, 2 of them, are using a calculator and the quadratic formula. These are the 2 we're going to focus on. Because I haven't done quadratics with you yet. Quadratics, to be honest, let's be very frank, they should be done first. I think quadratics are bread and butter, but I'm assuming that they are done and you're very confident with them. But quadratics are yet to come. I believe that will be the first lesson after I'm back. So something like, I might do it like a midweek session. I'm aware that we have the exam coming very shortly, but no, maybe we'll hold our nerve, and quadratics are going to be coming on the 4th of May. Yeah, when we get back to Saturday morning tonic. All right, so quadratic methods, let's write that up there as well, because this is for everyone who's looking at this file afterwards and would like to brainstorm. And we've exhausted 2. Well, it kind of gave us a result here that it was possible. So now we're not going to do completing the square. We're going to do the calculator. So if you've got the right calculator, that is. So if you're doing GCSE, you can get this funky calculator called the Casio FX991EX, and I've talked about this before in like best gifts for students. You'll see that in my video, and it really is a good one. We're going to go to turn it on, obviously, menu, and we're going to go down to equations, which I will call it as such. It's actually function A, and when we go into it, we get the option of simultaneous equation or polynomial. We're going to hit 2, which is a polynomial. And then it's going to ask us the degree. Well, a quadratic is degree 2, so we type 2. And all we have to do now is enter this. Now it's ax squared plus bx. Gosh, that looks like a 6. Make the 6 look more of a 6. And then plus c. And we're asked to input these coefficients. So that would be 3 equals 6 equals negative 8 equals. That's how quick it is. We'll press equals one more time, and the calculator tells us that x1 equals 0.91485542. And we press equals again, and we get the second. There should always be 2. Sometimes we don't want the negative one because it's a real life question and negativity is troublesome in real life. All right, so that's one way of doing it. The other way is the quadratic formula. This is a good chance to see whether you know how to do it, but ahead of when we actually do more work on that in the upcoming quadratics. So the quadratic formula is minus b plus or minus the square root of b squared minus 4ac over 2a, which will look something like this. Negative b being 6 in this case, plus or minus the square root of 36, subtract 4 times 3 times negative 8. Now, we've seen this before. We did this when we did our discriminant analysis. Not going to go into detail. 2 times a is 6. And if we churn that through, we get negative 6. The one version is where it's a plus. That plus minus means we have to do both. And 36 take away 4 times. Okay, so that's 132 because we did that earlier. All over 6. And you'll find that this is 0.914. Just like we had earlier. That's our x1. The other option here is negative 6 take away root 132. Because the only thing that's going to change here is the plus and minus. And that you'll find is negative 2.914, as you probably guessed. And there's your second option. So we've solved this equation. There's no context, so solving it means giving both. But I wanted to give you 2 options there. Now, what you really want to avoid is being in the exam, having this fellow here, and panicking. Because clearly you couldn't factorize it nicely in your head, so maybe you thought, oh my goodness, maybe it can't be done. But there are ways to stay calm, and I think that's the most important thing, is like just take a deep breath, reanalyze, and definitely know the full range of quadratic methods available to you, like so. And we're not going to go into all of them now, but we've done what we came here to do. We've practiced algebraic fractions. We did a little bit of quadratics as well. So that's a nice intro to quadratics because they're coming up later. Right, simplify the following fractions. So when you're talking about algebraic fractions, simplifying is the ticket to know, should we say. The ticket to doing that, talk about the turn of phrase, is I don't want ticket, I want factorize. Okay, so when it says simplify, that's the way to do it, because with algebra, well, there's no other way of simplifying, because they're not numbers. You need to find 2 things that multiply together that are on the top and the bottom. They have to be factors. Some people get caught out easily by dividing the top of the bottom by 5 just because they can see 150 and 5. And that's not, like, neither of those are a factor of the top and the bottom. They're being added or subtracted. So beware. Okay, so factorize. How do we do this? Well, I'm thinking, like, there's a really cool way to like on the calculator that we could learn right now, and why not? If I type in, because this top one looks very suspicious to me, like maybe 24 and 150, maybe there's a factor in there. So on my calculator, the FX991EX, if I just press a button called Shift, and in fact it's afterwards, and then there's a button which looks like this. See if you can find it. And at the top it has fact. Now it's not fact as in like a true statement. It actually means factors. And these are prime factors. So if I type 150 and then shift fact, it tells me the prime factors of 150, the product of primes. It's 2 times 3 times 5 squared. And if I do the same for 24, that's 2 cubed times 3. Absolute lifesaver. So I can see what goes into both of these. I can see a 2, but only 1. So the highest common factor definitely involves a 2. There's a 3 in both, but not a 5 in both. So the highest common factor is 6, which means I can take a 6 out of that top quite happily, and it's going to work out. So where to carry on working? I vote move this to the side. And perhaps here. So 6 times 4x squared, and something rather amazing occurs. It's that whole factorizing quadratic that we need to be aware of. Okay, so in this bracket, hopefully you recognize that difference of 2 squares. And we're going to make a note and park that there, come back to it. This denominator is suspiciously good. We can easily factorize this. There's a couple of ways of doing it, but I'm going to do it the proper full way, and why not? And if you follow it, that's great. If not, then we're going to be going through it in the quadratics, what do we call it? The quadratics Saturday morning tonic. Not forgetting that I do already have a quadratic series of videos. If you're hungry for more and you don't want to wait, they cover all of the quadratic methods that you're going to need, and probably a little bit more. So they're really fun and won't hold you back. But I'm going to use the AC method. I'll just have a quick drink. So the AC method is where we multiply the A and the C, and these two become 40. And we're going to look at all of the factors here. So 1 and 40, 2 and 20, 4 and 10, 5 and 8, yada, yada. And we're going to see that one of those pairs is going to get us to 22. Have you seen it? Yes, 2 and 20. So we're going to write this whole thing. I guess we'll just do this. And we're going to write this original quadratic as 8x squared. And instead of this negative 22, we're going to write it as a combination of 2 and 20. So in that case, it's going to have to be negative 2x and negative 20, because that's how you get to negative 22. And now we're going to factorize both sides. So we end up with 4x minus 1. And we're going to take out 5 here. 4x minus 1. So this is factorizing for you, just a basic linear factorizing essentially. I'll just put single bracket, and then we're going to factorize again. So we could see this subtract this. So 2 terms, and therefore in each of those terms that are being subtracted, there'll be something in common. In this case, it's 4x minus 1. And then we open a bracket to see what would be left, and it's the numbers on the outside if you want to trick. But you can verify that that works. So we've got our double brackets now. And we can put that straight. Okay. Now what we like is to have some continuity here with our working. So thankfully for me, I can have this move down. And this is what we call the AC method. It's a quadratic method for factorizing quadratics. But we're going to carry on with this one. So remember we said about the difference of two squares? We should notice that and be able to do it. We take this first term, 4x squared, and we square root it. And that's the first step. I guess the most important step is knowing that it's going to go into two brackets, like this. And then we square root the first term. The 4x squared gets square rooted, and that's 2x. And that goes in the front of both brackets. And the second term, which is 25, that gets square rooted, and that goes in the end of both brackets. One of them is plus, one of them is negative. This is in the quadratic series that I created. So please do have a look at that. It's a real fine method to be aware of. It comes up so much. And then, what beautiful. We have a bracket which matches in the top and the bottom. We didn't have factors before, but all of these things are being multiplied together, which makes each of those brackets factors. And we have one in the top and the bottom. So, to simplify, we simply cancel them out. 6, let's do that again. 6, 2x plus 5, all over the bracket that didn't cancel, 4x minus 1. And that's about it. You've came and conquered. So, this old question, this old chestnut over the page. Where are you? Tough, huh? Not beyond. You're used to being given an expression, and then that makes it easier, of course. But I just thought I'd throw in some modeling as well. So you're given a real life scenario and you've got to try and think on your feet. Now, there's some clues here because it asks you for an equation in terms of these letters. So you could probably assume that big V is volume because it usually is. And you guessed it, this is a rearranging equations question. It's I guess its pi is going to look like this, but it's hidden because you have to form it yourself. So if it's to do with volume, let's find an expression for the volume of this observatory. It's made up of, down here, a cylinder, and this would be a hemisphere, or a semi-sphere, depends how you like. And we're going to find the expression first, so let's call it V. We all know we're talking about volume. The cylinder is a prism, so the base is pi r squared, and the height is given as h. So that's the volume of the cylinder. And maybe I should have given you... No, we've done it in a previous video, so maybe we're okay. But the volume of a sphere... and you may have done this so many times now you remember it, is 4/3 pi r cubed. So the volume of a semisphere is going to be half of that, which would look something like, because you're going to add them together, it's going to look something like this: a half times 4/3 pi r cubed. Lovely, and we just need to tidy this up and take it home. You know, in the sense of winning. I'm just going to scroll down if I can. Right, tidying it up. What does that mean? Well, we've got fractions work. I've done plenty of this. I could tell you what topic we're doing at any given time. We have to tidy this fraction work up first because, well, just trust me. I'm a doctor. No, trust me because like you should know, when you make an expression simpler, you suddenly gain confidence. Like it just looks easier. So that's why we do it. We don't necessarily need these brackets now. And our aim, if we forgot, is to find an expression for pi. That's this here. That's this here and here. So it's in two places. And whenever you're in an equation, you get them into one place by factorizing. Okay, so this is going to come out like so. And don't worry about whatever's left. R cubed. This doesn't have to be tidied. Like you could probably factorize stuff out of here, but it doesn't matter because our focus is on pi. And so as weird as it looks, these two things are multiplying together. So just add a little multiply there, which makes them two factors. And it's as simple as this, people. It's like v equals 3x. And you want to get, actually let's make it with a number so it's even easier to see. You want to get x on its own, so you divide both sides by 3. Okay, how do you know to do that? It's because the right hand side is two factors. They're being multiplied together. So try and see it as simple as 3 times x. Okay, so, or in this case, x times 3, because we're going to be dividing by this whole thing. And if it makes it easier, like, why not? This will be in a video for the rest of YouTube's time. So let's just do it properly once. And everyone who's impatient can just forward the video. Why not? But I don't think it'll be that long. Busty. So both sides are going to be divided by this gigantic factor. And I'm going to even color it in. So it's this thing in here. And we're going to divide both sides by it. Color's always nicer, isn't it? Okay, so scroll down for some space. And we have our answer. Well, I don't like to have pi on the right, but I will keep it there. If we divide by this mammoth factor, we're left with pi on the right. And on the left-hand side, whatever was there, which is v, the whole thing, is going to get divided by that thing. Actually, I can paste it in, I think. Delay. Good old mouse works better. And there we go. We conquered. It may not be simplified, but we have it on its own, right? So this is now the subject, and when it says in terms of R, V, and H, essentially the other side needs to have R, V, and H only. You can't introduce new letters, and that's the case we have. Is there anything I wanted to add? I feel like there was one thing. Yeah, I guess that the only thing is, like, I probably wouldn't have written this. I probably would have jumped straight to putting pi on the left. Because in my head I can just imagine that the left-hand side is the same as the right. And so my answer is typically presented this way. But in that way, that's dangerous. Because if you're always expecting to see the subject on the left, you won't feel comfortable when it's not. It's up to you. Both of these are absolutely fine. All right, so let's move on to the next one, because this one is done. So simultaneous equations of the quadratic kind, but this one is not a bad one at all. A simultaneous equation just means that the value of x and y is the same in both. So these statements are true. So this value of x here is the same as this one here. And you could go ahead and guess some of these. it's okay if they're whole numbers, but typically they're not. And anyway, this one's pretty quick to solve. So essentially looking for equivalences. Now you notice that y is already on its own here. So we know that wherever we see y, it can be exchanged for x plus 1. So we look in the other equation. Oh, look, there's a y. So let's just write what could happen. The y in the first equation, so let's just focus on where we are here, can be replaced with this instead. And you take a moment to look at what happened there. That's a perfectly true statement. But what we've achieved is we've got rid of a y, and so there's only x. And that's really a revelation, because now we have one equation to solve. How do you solve this darn thing? You can't necessarily rearrange it. You should probably recognize that this becomes a quadratic because of the expansion. And there's only one way to solve a quadratic. We didn't necessarily go through earlier why you have to do it, but you're going to have to rearrange this. So we're going to take away 2 from both sides so that it's equal to 0. And now this equation is prime and ready to solve using quadratic methods. Now, the number one way of doing this is factorize. It's the quickest. So we'll look at both. So if we're going to factorize, there's one way of doing it, which is to say, okay, the 2 at the end, the negative 2, has factors that have to add or subtract to get the 1x, the coefficient 1 in the center, which is here. And how are we going to do that using 2 and 1? Well, it's 2, take away 1. So essentially, these are the values that go into the bracket. So x plus 2, x, take 1. And you can expand that to double check that that is correct. Now that's equal to 0 still. To solve a quadratic, we are using this factor method. We're going to figure out what would make this bracket 0. So if x was negative 2, then this whole bracket would be 0. And therefore, it doesn't matter what this bracket is. I know it's going to be negative 3, but it's going to be 0 because this first bracket's 0. And then what makes this second bracket 0 is when x equals 1. And therefore, if this is 0, it doesn't matter what this one is, it's going to be 0. So that's why we do what we do. That was a very quick recap. Check out the quadratic video again. Check them out. Like, there's the full method in there. It's like a series in the playlists of the channel. Very thorough. The other way is to use a calculator. And I'm not going to go into any other detail now because we've got a quadratic video coming up, but the calculator will give you exactly the same answer. So there you go. That's the first part of the question. Because, of course, these are just the x values. So you need to find pairs when you're solving here because there's 2 variables. So when x, and let's write when to jog your memory, when x equals, what was the first x? 1. Then y is equal to, well, it's very easy. I'm going to pick this bottom equation here. And as x is 1, that's 1 plus 1, that's y equals 2. So that's 1. Pair. And the second one was when x is equal to, was it negative 2, wasn't it? Yep, so that's negative 2 plus 1, y equals negative 1. Lovely. Beauty. Right. That's fully solved, by the way. So many people finish here thinking, yeah, I found x, but they need to pair it with y. And there you have it. These are really good questions. If I was like studying GCSE, I think they're really representative. I think these are good ones to jog our memories, and hopefully they're giving you some ideas of what you want to go back and look at. Okay, let's look at this last one now, and we'll give that a wrap before we have holidays coming. 5. Okay, so population of a town is growing according to the quadratic sequence 6, 15, 28, 45, 66. Where this is the population in thousands. So 6,000, 15,000, 28,000. We could just ignore the 1,000 until we conclude at the end. If the first term represents the population in year 2020, find the quadratic expression for the population in the nth year. That means that instead of the 3rd or the 4th year, we just mean any year. And to do that, it would be the nth year. And this n will be in place of a number. Anyway, let's see how it works out. I think a lot of people have seen nth term, right? Nth term allows you to find a generalization for a sequence based on the position. So if I wanted to find what was going on in the sequence, like a little bit down the road, and the 20th number, I'm pretty sure you couldn't figure that out very quickly. But with the nth term, I would get a formula. Let's say it's 3x squared plus x plus 11. In fact, it wouldn't be x, it would be n. And this formula is called the nth term formula. If I put 20 in, so 3 times 20 squared plus 20 plus 11, that will give me the 20th term, which I promise you is so much quicker than just counting up from the base. So, should we find that? This is a quadratic method. Okay, it's a quadratic nth term is slightly different. It relies on us finding the second difference. So that's what our first step is. We look at the difference. If this was a linear, then the difference between all of these terms would be the same. Well, that's 9, that's 13, that's 17, and that's 21. We call this row the first difference. Okay, they're not the same. So let's go to the second difference. So the second difference is 4, 4, 4. Okay, so that's where we're constant. You are dealing with a quadratic nth term if the second difference is constant. If we found the second difference, if we divide that by 2, we will find the a term in front of for the quadratic nth term. So if we had a n squared plus bn plus c would represent a general nth term, then the second difference divided by 2 equals a. Second difference divided by 2 equals a. Well, how do I visualize this? I actually set up a wee table. So my sequence is 6, 15, 28, 45, and 66. And my second difference revealed that it's going to be based on the sequence 2n squared. So what is n? I might put that here actually. N is 1, 2, 3, 4, 5. It's the position. So hopefully we're all up with the first step. We know that the actual sequence we have is based on 2n squared. It's whatever 2n squared is, and there's a little difference that will nudge it up to our sequence. So let's take a look at what 2n squared is. In the first box here, n is 1, so it's 1 squared, which is 1 times 2. In the next position, it's n is 2 now. So 2n squared is 2 times 2, which is 4 times 2, 8. In fact, let's get rid of the box. In the next position, n is 3, so that's 3 squared, which is 9 times 2 is 18. And we continue, and we get 32 and 50. Okay, so there's definitely the base. It's definitely increasing in a kind of similar way to the sequence that we want to know the nth term. And the best way to actually find that difference is to write it down. So the difference on how we go from 2n squared, which we know is the base, to our sequence 2 to 6, we must add 4. 8 to 15, we must add 7. We must add 10, we must add 13, and we must add 16 in order to get there. Clearly, we're not adding the same thing every time. If all of this was plus 4, plus 4, plus 4, plus 4, then our answer would be easy. It would be 2n squared plus 4. But unfortunately, the difference is a sequence in itself. This sequence, however, is linear, so it's a lot easier to deal with than a quadratic. So what we want to do is find the nth term of the difference, because it's what we add on is dependent on the n value, like the position. And to find, and we know this is linear because the difference each time is 3, 3, 3, 3, right? So the method I choose is dn plus a minus d. It's just a little formula that I use to find, and we're not here to work on the linear nth term, but so I'm not going to go into too much detail, but that's what I'm going to do. D stands for the difference, A stands for the first term, so that's going to be, difference is 3, so 3n plus, and the first term is 4, take away 3, which is 1. So this is the nth term. Let's write that down for you. Nth term. Nth term of the difference. So to get from the base, I'll write the arrow again, watch. To get from the base to our sequence, it's 2n squared plus 3n plus 1. I'll just colour that in so you know where things have come from. So 2n squared here is the base. We knew it was based on that. And we needed to add a sequence to it to get to the actual one. And that was this here. You could sort of label that whole thing if you want. And there's your final answer. There's essentially the quadratic expression for the population of the nth year. So if you put in, I don't know, 10 into this thing, you should end up with what the population is at year 10. Let's just test it out. Okay, so let's try it for 66. So we know that that's 1, 2, 3, 4, 5. That's the 5th term. So if we put n equals 5 in there, it should be 66. And that's 25 times 2, which is 50, plus 15, which is 65, 66. It is. So when n equals 5, 66,000 people. So we can essentially use this to put in what we want. That leads us to the next question. What's the population in 2043? That's going to be related to the fact that the first year represents 2020, and we want to find 2024. This formula allows us to put in the number of years. So we just have to figure out how many years it's been from 2020 to 2043, and you might be surprised. So just be very careful and hold on to your hats while we do this one. This is going to be relevant. And essentially, this is equal to P, the population. If I put in n equals 20, I would find a population in 20 years. What are we going to put into this question? Now, sometimes it can play with your head. So I think the best thing to do is to just write it out fully. So 2021, I had this all planned out in a way that hopefully, if you were struggling, like you were stuck, you would write a few out. You wouldn't just panic and think, oh, I just can't think about this. You would go to your very basics and write it out and see if there are any patterns. So anyway, there's a few years to start working with. We know that this represents the first year. Right, so in our sequence, this, if we put 1 in, this would give us the population in 2020. And so let's say we go to 2026. That's 1, 2, 3, 4, 5, 6. 2026 would be 7, 6, 5, etc. And using 2025 as an example, this one here, that's where n equals 1. We know that 2025 is going to be 1, 2, 3, 4, 5 years later. So that's 2020 plus 5. And what does 5 represent? Like how many years later? Like what does 5 represent in terms of our values of n? Okay, so as we're talking about here. Well, it's whatever n is, which is 6 minus 1. So that's going to be 2020 plus n minus 1, 6 minus 1. So if we conclude that, therefore 2043 is going to be 2020 plus n minus 1. And therefore we can conclude that n is 24. We could do it in a number of ways. We could rearrange the equation, right? So I'd probably find n by doing 2043, take away 2020, which gives me 23, and then n equals 24. Now, it doesn't seem initially very obvious to me. It's just the fact that the question said that the first year was 6,000, right? So that was what I defined as 1. So maybe you would have thought that you put in 23, but 24 is going to be the one to use here. So the population, we could even call it population 2043, is going to be 2 times 24 squared plus 3 times 24 plus 1. I did a little bit on a calculator there, and we're going to get something ridiculous. 1, 2, 2, 5. Okay, and that is actually the value, but if we go back to the original question, that's in thousands. So it's actually 1.225 million. And that's only a prediction. Okay, so technically you could do this. And maths is all about assumptions. Why do you think there are so many assumptions in maths? There are so many assumptions because maths isn't particularly about real life stuff, okay? Maths is conceptual playing with abstract numbers. And we like it. We can see these numbers in real life. But as far as we're concerned, like there's too many variables that are chaotic and out of control to really fully model. Generally, humans are so inaccurate, we just want the average of things and round it to a few decimal places, and that's pretty much all. And so most things are assumptions, things that we're not fully in control of. This is one of them. When the population grows, you know, anything to do with patterns, and this is why we love statistics so much. It's the only real science that we have to deal with the future of things. But even that's not an exact science, because the future is the future. Anything can happen. All sorts of things change, and you may think that you have a pattern. It very easily won't continue. And that's, I guess, a chat for another day. But I'm just thinking on the top of my head, where you have, where you have data, for example, and it's measured like in this region. and let's say you make a prediction that it's going to continue, there's actually no guarantee that it will. This is much safer to make predictions in here. Anyway, as I said, I'm not going to get diverted. Thanks for coming along today, and this is how you answer this question. It's a quadratic sequence in context, and as I said, I won't be around for next weekend, but I will be uploading to my Patreon a pretty cool set of questions that I think everyone should be able to do as a basis to just double check that you have all those core skills in place. If you're missing one of them, I highly recommend sorting it out, because maths is a hierarchical subject. Just going to draw you a hierarchy to visualize what I mean by that. So, a pyramid. And I think you'll appreciate that if you had one of these base, you might not be doing too bad, but if you had a couple of those bases, or even 3 missing, this whole pyramid is probably coming down. It's very hard to balance these higher bricks without this base knowledge. And this base knowledge creates a hierarchy, which is there called hierarchical. And I've hopefully put probably the first 2 layers of the base of knowledge of mathematics GCSE into one document, and hopefully you'll take off. You may be struggling with so many different areas of maths, and all it takes is one brick to come back in place. Just one little thing that you couldn't believe sometimes how small it is, and then all of a sudden all of it makes sense, and you can support all those bricks up top. Anyway, that's a motivational ending, and happy holidays. I don't know what you're doing, if you're holidaying, where you are in the world, but best of luck, working hard, and reach out if you have any questions, and I'll see you in the next one.